In this lesson, we will discuss the real number system. Now in this lesson, we have many different definitions and terms to discuss, and then we also have different notation to be aware of as well. All right, so jumping into our definitions, we have first off what we call a set. A set is simply a collection of objects. All right, so it could be like a set of basketballs, or it could be a set of numbers. It could be a set of any type of object. Now we have what's called an element, which is an object in a set. All right, so if you have a list of numbers, let's say the number 3, for example, would be an element. It is an object inside of a set. Now with sets of real numbers, we have what we call natural numbers, and this is what you think of when you think of counting. All right, you start with 1, then you go 2, 3, 4, 5, etc. So it starts at 1 and is counting up from the number 1. And then we have what's called whole numbers, which includes all the natural numbers, but also adds the number 0. A way to remember that whole numbers includes number 0 is if you look at the word whole. Okay, whole could be spelled with just H-O-L-E, so different spelling, different meaning, and the number 0 looks like an actual whole. All right, so the whole numbers includes number 0. And then we have what's called integers, which would include all the whole numbers plus the negative numbers. All right, so it's going to be something like this. And notice, by the way, there's no fractions included for any of these. All right, so integers would be 0 and then 1, 2, 3, etc., and then all the negatives of those natural numbers. And then we have rational numbers, which includes all of the listed numbers above. It includes all the integers, but it also includes fractions, and it includes the decimals that do not go on forever without repeating. So for example, something in this format where you have P over Q, where P and Q are integers, anything that can be written as a fraction would be a rational number. So this could include things like, say, 4/5, or it could be a negative even, it could be negative 7/9. It can include decimals such as 0.6, or it could include decimals that repeat, so it could be like 0.6 repeating. What would not be included in that would be irrational numbers, which cannot be written as a fraction, which would include things like this. So it could be a decimal that keeps going on forever without repeating, or that would include numbers like pi, for example. So pi is 3.14, etc., goes on forever, or the natural exponential e would also be irrational because that's a decimal that keeps going on forever. All right, so those would all be irrational numbers. Another way to visualize this would be with the following diagram. Here we have natural numbers. Remember, it includes 1, 2, 3, 4, 5, all the way counting forever. Then whole numbers, here in this notation, in this diagram, we have whole numbers would include the natural numbers, but also adds the number 0. And then integers would include everything inside of it, so it includes the whole numbers and natural numbers, but also includes the negative numbers. And then rational numbers includes everything we see inside. It includes integers, whole numbers, natural numbers, but also includes fractions, whether positive or negative, or it could include decimals as long as they do not go on forever without repeating. And then over here on this side, we have irrational numbers, which would be anything that's not rational. All right, so rational and irrational are two totally separate categories, which, by the way, irrational numbers could also include radicals or square roots that are not perfect squares. So like here, square root of 2 is not a perfect square. This would be an irrational number as well. All right, so make sure you know the difference between those different types of numbers. Now moving forward, we have some more definitions, and this is when we deal with sets. All right, so we said a set is a collection of items or elements. Now we have what's called a subset. Now a subset, here's the definition. It says set A is a subset of set B if all the elements in set A are also in set B. And here we see the notation for that. Now what that would look like would be, let's say A would be something like this. You have 1, 2, 3. And let's say B would be 1, 2, 3, 4, and 5. We can say that A is a subset of B. That's the notation, because every element here in set A, the numbers 1, 2, and 3, those are also elements in set B, right? It's just a smaller set. It's a subset. It is part of set B. So we say set A is a subset of set B. Next we have what's called an empty set, or in other words, a null set. And this is a set that contains no elements. And we see here the notation for an empty set. All right, so that would be a set with nothing in it. Okay. And then we have what's called a finite set. Finite is the opposite of infinite. So infinite would be something that keeps going on forever, where we cannot list all the elements, right? Because it keeps going forever. It never ends. Whereas finite, that is the opposite of infinite, and there is a definite end. There's a limited number of elements. So for a finite set, all the elements can be listed because it does have an ending point. All right, and then we also have this notation right here. This is a fancy E. All right, such a kind of a weird looking E. And what this means is it means an element of. All right, so we're going to work with this here in a moment. So these are our basic definitions for sets. And then we have what's called set builder notation. So here is an example. All right, notice we have braces around our entire expression. And then we have here, it says 3x. So this would be 3x, and then this vertical bar right here means such that. All right, so we have 3x such that x is an element of the real numbers. Another way of saying that would be the set of all elements 3x such that x is an element of the real numbers. So what this would look like would be you plug in real numbers for x, and whatever you get back out when you plug it in here into 3x, that's going to be your set. All right, so that's kind of the idea behind that. And here's another expression. We have this right here. It says x, or the set of x such that, that's this vertical bar. So x is an element, or sorry, the set of x such that x is less than 5, where x is an element of integers. So again, what this would mean is that we plug in integers in place of x, and we plug it in over here. And whatever numbers we have where x is less than 5, that's going to be your set. And here we see it written out, the set of x such that x is less than 5, and x is an element of the integers. So if you list out this set, it would be something like this, where x must be less than 5 and x must be an integer. So it could be things like 4, or it could be 3, or it could be 2, it could be 1, it could be 0, it could be any integer. And it cannot be fractions, because integers does not include fractions. But this would keep going on forever. All right, this would be an infinite set. So it's going to look something like that. So that's the idea behind this notation. It's a shorthand way of writing this longer expression. Now, some other concepts of dealing with sets. We have what's called unions and intersections. So here, we say a union of set A and B. The notation looks like this. So A, and then this U right here, U for union. So A union B, so A union B. And what this means is the set of all elements that are in either A or B. So in other words, it's combining the sets. All right, so for example, if set A has 1, 2, 3, 4, set B has -1, 0, and 1. If you were to find the union of sets A and B, you see that here in the notation, you're putting together all these elements. So you have the 1, 2, 3, 4, we see right here. Then you put in the -1, 0, and 1. So -1, 0. We had 1 already listed, so no need to write that twice. But you put everything together, and this would be your new set. So that would be union. And then intersection is where they overlap. So intersection, the symbol, is an upside down U. All right, so it's the opposite of union. And for this one, we need all the elements that are in both A and B. They need to be intersected, or where they overlap. So here we see the same two sets. We have set A and set B. Now the intersection of them is, what do they have in common? Where do they overlap? Well, notice they both have a 1 in common. So the intersection of sets A and B would be the element 1. So that is your new set. So we have unions, we have intersections. We also have what's called disjoint sets, which is when two sets have nothing in common. So the symbol here means therefore, by the way, the 3 dots. So therefore, if you were to intersect sets A and B, it would be an empty set. There's nothing in common. So that'd be something like this, where you have A would be 1, 2, 3. And then set B would be 4, 5, 6. If you intersect sets A and B, and you see what they have in common, notice there's nothing in common. Right? There's no numbers that are the same. So that would be an example of a disjoint set. Now, still on the topic of sets, we have what we call interval notation, and we have set builder notation. So set builder notation is what we've been dealing with on the last few slides, where we have something like this. We have x such that -2 is less than x, which is less than 5. So if you look here at this part, we've dealt with this in the past in our study of algebra, where we know that x is between -2 and 5. Okay, if you were to look at this on a number line, okay, if you put this on a number line, we have -2, here's 0, 5 is somewhere over here. If you were to graph this, it would be an open circle at -2, open circle at 5, and it's going to be everything in between, because x is between those two things. So you shade in everything in between, and this would be your graph. So we see it's between -2 and 5. That's your values of x. And in interval notation, we would write it like this. So we have -2, 5, and the parentheses is kind of the same thing as the open circle. So if you were to compare that with this next example here, where you have -2 is less than or equal to x is less than or equal to 5, okay, that's different because when you graph that, instead it's going to be a closed circle, right? So that's going to be a closed circle, and in interval notation, we would write it like this. We write it with these braces, or I guess brackets right here. All right, so you put brackets around it in this case to indicate that it reaches -2, and that's the idea of it being a closed circle instead. All right, so we see this other example right here where you have a combination of a less than and a less than or equal to. So in interval notation, we still have -2, 5, showing it goes from -2 to 5. But where we have just a less than symbol, it's going to be the parentheses on this side, and then here with a less than or equal to symbol, it's going to be a bracket on that side. So it's a combination of a parentheses and a bracket. And here's another example where we switch, where now we have a less than or equal to and then a less than. Same idea, where the less than or equal to sign can be translated over here in interval notation as a bracket, and then this less than sign for the 5 can be translated as a parentheses. And again, this notation over here in interval notation simply means that we have the values from -2 all the way to 5. And then we just determine if it's going to be a bracket or a parentheses on the left and the right side. Now here's another example where we have x such that x is less than 5. So this one, if you were to graph this one on a number line, okay, we have 0, here we have 5. This would be an open circle at 5 shaded into the left. Okay, so that's going to be how you graph that. Now in interval notation, because it keeps going on forever and ever and ever to the left, okay, it's going to go on for infinity in this direction. So that's a sideways 8. That's our infinity symbol. So it's going to go from infinity all the way to the number 5. So when you write this in interval notation, we write this, and actually make sure you realize this is negative infinity, because it's going on to the negative direction. So we put a negative symbol there, showing that it's going infinitely to the left in the negative direction, and then comma 5. Now, anytime you see infinity, you always put a parentheses on that side in the interval notation, because the parentheses means we never actually reach it, right? You can never actually reach infinity because it keeps going forever, so we put a parentheses. Just like we do with the open circle, because we never actually reach the number 5, we get infinitely close to it, but we never actually reach it, which again is why we put the parentheses. All right, that's the notation for the open circle. And now one more example on the slide. Here we have x such that x is greater than or equal to 3. So again, for this one, if you were to graph this on the number line, okay, here we have 0, here we have 3. It's going to be a closed circle at 3, and we shade into the right because it's greater than or equal to. All right, so we start at 3, and we're going all the way on to infinity in the positive direction. So it's going to keep going on forever. So with it going on forever, we put a parentheses around. And then here, because it stops at 3, we put a bracket over on that side. So in interval notation, we have this as 3, and then all the way to infinity. And again, just take note, we mentioned this, but make sure that with the infinity symbol, if you're going on to infinity, always use parentheses, not brackets. And also, it's worth noting that you could, if you want, for this example here, when you're graphing with a closed circle, we could graph another way as well. So we could graph the same thing, 1, 2, 3, where instead of a closed circle, we can actually use the bracket and then shade in over this direction. All right, so we can also do it like that at times. So it depends on what you prefer. It's the same thing, really. And then if you have the open circle, so let's say we had this 1, 2, 3, say it was an open circle shading into the right, you could also graph that with a parentheses there instead of the open circle. So you could do it like this, where you have a parentheses and then shade in that direction. All right, so both are okay, and both mean the same thing. Okay, now we're switching gears a little bit. So we're getting off the topic of sets, and now we're going to talk a little bit about absolute value and distance. So absolute value, we have this notation right here. So let's say we have the absolute value of A. Okay, don't get overwhelmed with this math notation. Okay, basically what this means is that you make the sign positive no matter what. So let's say you have the absolute value of -4. It's going to be positive 4. Absolute value of 4, positive 4, would still be positive 4, because absolute value means distance from 0. So -4 is 4 away from 0. Positive 4 is also 4 away from 0. Over here in this math notation that we see, I want to make sure you understand how to interpret this. So if A is greater than or equal to 0, that would correspond with this part right here, right? Because the number 4 is bigger than 0. If it's bigger than 0, it's just going to stay the same. It's going to remain as the number a. But if a is less than 0, which would be like the -4 up here, if you put that in the absolute value, what happens is it changes the sign. It's going to become a -a. So if it was a -4 on the inside, now it becomes a -4, which would be a +4. So that is showing that it's changing the sign if a is less than 0. So bottom line, absolute value is always going to be positive. Now, absolute value, we said, is the distance from 0. So speaking of distance, if you had to find the distance between 2 points, okay? So the distance from A and B, and we see that notation here, D for distance. A and B are the two different numbers, and keep in mind this is on the number line, so this is not ordered pairs, but on the number line. What you do is you subtract the two numbers and make it positive. So for example, if you had to find the distance between the points -5 and 4, so here's -5, here's 0, here's 4, you want to find the distance between those two, you can think through logically if you want. From -5 to 0, that distance is 5. And then from 0 to 4, it's going to be 4. So if you take 5 plus 4, we get 9. All right, so we see that conceptually. But what you can do is you can simply subtract the two numbers, -5 and 4, right? -5 minus 4, that gives you -9, and just make it positive. So if it's a negative, make it positive. If you subtract it the other way, 4 minus -5, that would give you a +9, and just keep it positive. So the order of subtraction does not matter as long as you take whatever number you get and make it into a positive number. Now, switching gears again, we want to discuss what we call exponential notation. So here we have an example of the number 2 multiplied 5 times. In exponential notation, we can write this more simply as 2 to the 5th power, where the base would be 2, it's a number that's being multiplied over and over again, and then your exponent would be, in this case, the 5. And by the way, notice the 5 is a superscript. It is a smaller number, and it's written above the 2. So when I say smaller, it's smaller in size. So it's written smaller. All right, and the 5 is how many of those numbers are being multiplied together. So because we have 5 2's, it's going to be 2 to the 5th power. Now be careful if you have a negative number raised to a power. Make sure you're following order of operations. So remember order of operations. We have parentheses, exponents, multiply, divide, add, and subtract. So following this order, we want to do exponents first. So what you do is raise 3 to the 4th power first, and that gives you 81, and then do the negative after to get -81. And that's different than if the -3 were in parentheses. So if you have -3 to the 4th power, where the -3 is in parentheses, what that means is that we have -3 multiplied 4 times. So when you multiply the -3 4 times, 4 negatives, when you multiply, it gives you a positive number, and that would give you a +81. So just be careful when you have a negative and you have an exponent. So we've mentioned, order of operations right here. Now a little more in detail of this process. All right, if you are working with the parentheses or the grouping, all right, so that would include parentheses, could include brackets, could include braces. Okay, make sure you realize all of those would be parentheses. So grouping or parentheses. And then we have exponents would come next. So we have parentheses, we have exponents, which by the way would also include radicals. And then we have multiplication and division. Those can be done at the same time, but you work from left to right. And then we have addition and subtraction. So those again can be done at the same time, and you work with those from left to right as well. And the mnemonic, or the way to remember this, is please excuse my dear Aunt Sally. So PEMDAS, that is the order. All right, so let's take a look at an example of this. So here we have many different things going on. And when you start with parentheses, that's the first thing you begin with, you want to work with the innermost parentheses, or innermost grouping. All right, so here in this example, we see brackets, and then we see parentheses. So right here, this is the innermost set of parentheses. It is inside of the brackets. So we start in here, and within here, we want to do exponents before you do the addition. So we do 3 squared first, which gives you 9, and then we do the addition, 9 plus 11, which would give you 20. All right, now from here, we've taken care of that parentheses, but we still have this bracket here, which is a form of parentheses. So now we work inside of this, and we have exponents, which we don't have in this case. So next we would have multiplication. So multiplication, we would have 10, 5 times 2 is 10, and then division. So we do 20 divided by 5, which is 4. So we have 10 and 4. So we have 10 minus 4 inside of the brackets. 10 minus 4 is 6, and then 3 plus 6 gives you 9. So your final answer in this example would be 9. Now switching gears once again, we want to discuss variable expressions. So variable expressions would be something like this, and variables would be anything with letters in it, all right, where the letters stand for some unknown number. With an expression like this, we have different parts. We have what's called terms, and that would be anything separated by a plus or minus sign. So like here, 4x squared would be one term. Then we have here negative 6xy, that would be another term. And then we have a positive y right here, that's another term. And then negative 27, that is a fourth term. So this example here would have 4 different terms. All right, and then your variable terms would be any term that has a letter in it. So like 4x squared, negative 6xy, positive y. Those 3 would be variable terms. And then you have, within those variable terms, we have what's called coefficients, or numerical coefficients, which would be the number in the front. So the coefficient of 4x squared would be the 4. Coefficient of negative 6xy is the number negative 6. And then the coefficient of y would be an assumed 1. There's an assumed 1 in the front. So that would be the coefficient of that third term. So we have 4, negative 6, and 1 would be the 3 different coefficients. And then the variable component would be the part with the variables. So we have, the x squared would be a variable component, xy would be a variable component, and then y right here would be a variable component. And then the number by itself is called the constant, or the constant term. So a constant is something that does not change, which would be a number. A number does not change, right? 4 will always be 4. 5 will always be 5. All right, so the constant is the number part by itself. Now with variable expressions, we can simplify at times. So we have 2 examples to look at. And first, with example 1, we have this expression. And what you want to do is you want to try to distribute first. So see this 4 in the front? You can distribute or multiply to both parts in the parentheses. So when you do that, you have 4 times 3x, which gives you 12x, and then 4 times negative 5, which is negative 20. So if we, from here, we can combine like terms. So like terms would be things that look the same. So like here we have 2 and negative 20. Those are like terms because those are both constants. So if you do 2 minus 20, we get negative 18. So we have 12x minus 18, and that is as far as we can simplify. That does not go further because 12x and negative 18 are not like terms, because this here has an x, 18 does not have an x, so those are not like terms. Example 2, we have this expression. Now this one looks a little more complicated, but notice we have braces and then we have parentheses. You want to work on the innermost grouping. So we see here this 3x minus 6, we want to start with that. And this negative 2 can be distributed to both those. So we have negative 2 times 3x, which gives you negative 6x, then negative 2 times negative 6 gives you a positive 12. All right, and now from here, we could simplify inside of the braces if we wanted, or we could just take this negative 4 and distribute again within this grouping. So if we do it this way, we have negative 4 times 5, which gives you negative 20. Negative 4 times negative 6x is positive 24x. And the negative 4 times 12 is a negative 48. Now, once we get to this point, we want to look for like terms. So here we see 3x and 24x. Those are like terms because they have the same variable component. So we can combine. We have 3 x's plus 24 more x's. That gives you 27 x's. And then we can combine negative 20 and then minus 48. And that gives you a negative 68. So this here would be your final simplified answer of our original expression. Now, switching gears once again, we have talked a lot about numbers in this particular lesson. That was the topic, was real numbers. And so dealing with numbers, okay, we have properties of real numbers that will help us to perform different operations. So here we see a little chart. So we're going to let A, B, and C be real numbers. And we have addition properties and then multiplication properties. So our first property is the closure property. And basically what it says is that when you're adding, if A and B both are real numbers, when you add them together, it will still be a real number. So it's the idea of you begin with a real number, you're going to end with a real number. And by the way, the answer is unique, meaning there's only one solution. With multiplication, same thing. Our closure property of multiplication says if A is a real number and B is a real number, then when you multiply, you're still going to get a real number. And again, it's going to only have one solution. It's going to be unique. So that is your closure property. Next, we have the commutative property. Commutative property says for addition and multiplication that the order does not make a difference. So for example, for addition, A plus B is equal to B plus A. We can interchange the numbers. That'd be the same thing as saying something like 4 plus 5 is equal to 5 plus 4. The order does not make a difference. Same thing with multiplication. A times B is the same thing as B times A. Again, that's the idea of something like 4 times 5 is equal to 5 times 4. The order does not make a difference. Next, we have the associative property, and this is dealing with the grouping. So for addition and multiplication both, the grouping does not make a difference. So for addition, let's say we're adding 3 numbers, A, B, and C. It doesn't matter if we group and add A and B first, and then add C, or group and add B and C first, and then add A. The order does not make a difference, or the grouping does not make a difference. With multiplication, same thing. If you have 3 numbers multiplied together, it doesn't matter if you do the first 2 numbers multiplied first, or the last 2 numbers multiplied first. The grouping does not matter. All right, so that's your associative property. And then your identity property says that there is a number, and then for addition is a number that can be added that does not change the identity or value of the original number. And that number that we're adding would be the number 0. So if you start with a number and add 0, 0 does not change the identity or the value of the original number. You start with A, you're going to end with A. For multiplication, it's a different number, and that number is the number 1, because anything times 1 gives you the same answer back out. Right? If you started with 5, you multiply by 1, you still get 5 back out. And that's the idea of the identity property for multiplication. Now the inverse property is the idea of something happening or something being done to get back to the identity. All right, so for addition, to get back to the identity, or to get back to the number 0, you have to add the inverse. So if you have A and you add it with its negative, which is the inverse, you're going to get back to 0. that would be something like 4 plus negative 4, or 6 plus negative 6, or negative 8 plus 8. If you take a number and add it with its inverse, we get back to 0, which was the identity. For multiplication, on the other hand, to get back to the identity, which would be the number 1, you want to multiply by its reciprocal. So if you take a number, we'll call it a, you multiply by its reciprocal, which would be 1 over a, that would give you 1 back out. So a reciprocal, if you take a number, say like 3/5, the reciprocal would be switching the top and the bottom. So like 5 over 3. And that would give you back out 1. So that idea there is your inverse property. And then we have what's called the distributive property. This is not really categorized under either addition or multiplication. It's kind of its own thing. And we've discussed this on the previous slide when we're simplifying. But your distributive property says that we can take a number outside of the parentheses, and then we can distribute or share it to the different terms inside of the parentheses. So you do a, whatever this number is out here, you multiply it by the first term to get a times b, and then you multiply it by the second term to get a times c, and then keep the sign the same in the middle. And this could be extended for any number of terms in the parentheses. We can distribute over and over with 2, 3, 4 terms, and etc. Now to finish off this lesson, we want to discuss properties of equality. So again, we're going to let a, b, and c be real numbers. And our first property is called the reflexive property. And this says that a is equal to a. So it's just stating that a number, some value, is equal to itself. So it could be 4 equals 4, 8 equals 8, or something like that. And then we have the symmetric property, which says that if a equals b, then b would equal a. And this is used many times when solving equations. You might get the answer of 4 equals x when you solve. You can switch that around and write that as x equals 4. So that would be sometimes when you use the symmetric property. The transitive property is right here, and it says if a equals b and b equals c, then a equals c. So this is kind of like a train. So if a is connected with b, and then b is connected with c, then a and c are connected. And we see the word transitive kind of sounds like the word train, and that's the idea of everything being linked together. And then we have the substitution property, which says we can replace something with an equal value. So for example, if a equals b, then a can be replaced with b in any expression that involves a. An example of this would be, let's say, if x equals 3, and you're told that, or you're told to find or evaluate, so evaluate, let's say, 2 times x. Based off the substitution property, anywhere I see an x, I can put a 3. So here is an x, I can put a 3. So instead of 2 times x, we have 2 times 3, and that could be solved to get 6. All right, so that would be your substitution property. All right, and that concludes our lesson for today. We've covered a lot of content, a lot of terms, so do brush up on these and make sure that you understand this, because as we move forward, we're going to have to use these different concepts. So I hope you found that helpful, and we'll catch you in the next lesson.